Yes. Well, today our main emphasis is going to be on currents and circuits. And we have to move along, unfortunately, fairly quickly, so I may have to slide over some things to get along. You see, but first, actually, I wanted to touch up a couple of little things. Keep going back to what we didn't quite do last time, namely potentials. There's just a couple of points I wanted to make on that. Namely, just to make the points that I want you to be able to distinguish between fields, scalar fields, well, not even that. The idea of something per unit charge versus something that has the full quantity to it. For example, we have energies which is the potential energy is equal to Q times V. Oh my God. This I better save for later. Yeah. But you also have the energy per unit charge, which we call V. It's U over Q. Then we also have the field, which is the force per unit charge, and we also have the force. And the relation between these is that the energy is equal to a minus the integral of the force times the distance, or that the change in the energy over a distance is equal to a force minus. In other words, this is the gradient or the rate of change of the energy. The rate of change of the potential with respect to a distance is equal to minus the electric field, and the integral of these things, for example, the delta V is equal to minus the integral of the electric field times the distance. You want to make a distinction between a field and sort of the total quantity, the energy or the force. See, these are the things we really measure. These are kind of constructs. These are the fields set up by some agglomeration of charge, which you might call, again, the pushers. They push on things. This is the interaction of the field with the pusher. In other words, it's with the field with a pushee. So in other words, you have to put something in there to feel these fields, and then you'll get an energy, namely a speed or something like that coming out, or a force. You'll feel a push or a pull on something. So please have these concepts in mind. The other point I wanted to make is just to do a quick number for what does it mean a volt. Suppose, you remember, some of you weren't here on Friday, but what we did on Friday was to show that if you have a kind of conducting fluid, I used a lemon, an orange, and a banana. The class, or The classic thing was a frog's leg way back when. And if you put two different kinds of metals, metal 1 and metal 2, like iron, say, and copper, in here, what you get is that you actually get charge trying to move through this between the two metals. And if you give them another path through here, actually, they'll actually run through here and can deliver some energy to you, because they're trying to go from a high energy to a low energy state. In so doing, they give up their energy as you go along. This is the origin of what's sometimes called a battery. Actually, it could be called a cell, because it's only one of them. Truly, a battery, like a battery of tests, is not just one test, it's a whole series of tests. So a battery really, it really means a bunch of cells, connected. That's a true battery. But one of these would be just a cell, but that's a, nitpicking way of looking at the word. But so a typical dry cell looks something like this, and that's just one cell, and between here and here is 1.5 volts. That's your typical common dry cell. If you buy a battery, a 9-volt battery, as it were, then if there's 9 volts here, you can be pretty sure that what you have inside is 1.5 volt cells in series, a series of them. So this is genuinely a battery, because it's a whole series. So that's 3, 6, 9. So you'll have 6 times 1.5 volts inside a 9-volt battery. I just passed that along. I don't know if it probably won't appear on the test, but you can remember it anyhow. It's nice to know. And for example, in your automobile, you have a 12-volt battery. There are a bunch of cells, no one of which is 12 volts. There's just a whole bunch of them in series, giving you a total of 12 volts. So that's genuinely a battery made up of a series of cells. Okay, but we built out of a lemon or a lime, or just two different. The important thing is that two dissimilar metals, iron and, say, copper. And a voltage is created across there. We saw it on a meter, and it provides. This, as I said then, last time, and those of you who didn't hear it should hear it again. This is the crucial step in making electricity practical, because Volta, who discovered this and published a very good paper in 1800, astonished the world by saying, I can provide you electricity on demand, and with a fixed amount. I can tell you how much it will be, and reproducibly every time, by putting a series of dissimilar metals in a row, and you can create a nice big push of current through things. And that was the beginning of an avalanche of great discoveries, because now electricity, which up to that point had been just a curiosity, became a controllable thing that you could do science with. Tremendous discovery. But let's see just what does it mean to have a 1.5 volt battery or cell. So suppose, for example, I took such a thing and put it across my usual conducting plate, say, and let's just take 1 volt for the simplicity, although typically it's 1.5. Okay. So let me just, for fun, see what happens if, for example, I put a 1 volt level here, and this is the negative side. Really, it's a 1 volt difference. You can call this anything you want. You could call this 5, but this then would be 6. It doesn't matter. It's the difference that counts. Because what's going to happen is, for example, and if I call this side plus, this plate will become plus, meaning that negative charges will run down over here, negatives will run away from here, leaving behind an equal amount of plus Q on here and minus Q on here. So that's physically what's going to happen. Now, suppose, for example, I introduce in here by some means 1 electron. a negative electron at this plate here at 0, or at this position. Now, it sees up here these plus charges, and it sees down here these negative charges. So it's going to be repelled by this plate. Well, a fancy way of saying it is that there's an electric field this way, and because this is negative, it runs against it. When left alone, it would run up the electric field, which is another way of saying it's attracted to the plus plate. But we can use our idea of potential and potential energy to find, this is what I'm after, is the final speed if that electron were released and flew up to the top plate. I think it'll come out an astonishing number, like 1,000,000 miles an hour, which would be shocking, I think. But let's see. What the law that we will use is the conservation of energy, namely that the kinetic energy plus the potential energy from at the end, say, will be the same as the kinetic energy plus the potential energy initially. Okay, so let's just see. So initially, if I just put this negative charge here at 0 speed, so I just managed to get it in there, but I hold it there, and then I release it. So its initial kinetic energy is 0. And I'm also going to define the 0 potential energy when I'm very near that plate. As I say, I could call it 5, I could call it anything I want. The point is the change will be that. So let me, for sake of our simplicity, just say the potential energy initially is also 0. Okay, now the thing flies up, and it achieves some kinetic energy, which we don't know yet, a half mv final squared, plus the potential energy. Okay, now the potential energy is the voltage change. This is what I wrote a little while ago. Potential energy, or U, is equal to a QV. Now, my V has gone from 0 to 1. So, or you might even say delta V. So delta V in this case is 1 volt, right? Plus 1 volt. Because that's the potential, is 1 volt. Then I multiply it by the charge, Q. Well, it's actually minus the charge of the electron. Q is equal to minus the charge of the electron, which is minus, that's been measured, 1.6 times 10 to the minus 19th Coulomb. Okay, so the change in the potential energy, or the potential energy at the end, is minus 1.6 times 10 to the minus 19th coulombs times 1 volt. The change in the potential. So I put that in here. That's the final potential energy. Minus 1.6 times 10 to the minus 19th times 1 volt. This, by the way, we call an electron volt. So that's the energy of the energy change, an electron, specifically an electron with this charge. This is the energy change it will undergo when it moves through 1 volt. It's 10 to the minus 1.6 and 10 to the minus 19th, and the unit is joules. Okay, so we then have the result here that if we solve for Vf squared, and you see the minus, we'll put that on the other side, because that's equal to the sum of these two, which is 0. So the Vf squared is, now the sign has changed because I put it on the other side, 10 to the minus 19th, and I have to multiply by 2. this 2, and I have to divide by m, the mass of the electron, which I looked up, and it looks something like 10 to the 9 times 10 to the minus 31 kilograms. Happens to be the mass of the electron. Okay, so to get the final velocity, I have to take the square root of this. And let's see, 2 times 1.6 is about 3.2, and that's 10 to the minus 19th. Now there's 31. Let me make this into minus 21 and multiply by 100. This just does the arithmetic a little easier. 10 to the minus 31. So you see those sort of cancel with the power of 10 coming up. And 9 into 300 is about, let's see, you actually have it worked out here. What? It's something like 35, square root of 35. And you have 10 to the 10th here. Okay. So, this is where this number comes out really kind of amazing. VF final, the final velocity, will be square root of 35, which is around 6, times square root of 10 to the 10th is 10 to the 5th. That will come out in meters per second. So that is, if you want to make it into kilometers, there's 10 to the 3 kilometers in 10 to the 3 meters in a kilometer. So that would be about 600 kilometers per second. If you want to change it into miles, there's about 1.6 kilometers in a mile. So that's going to reduce to miles. It's 400 miles a second. And if you want to make it into miles an hour, you multiply by 60 seconds in a minute and 60 minutes in an hour. That's the way I do it anyhow. You may have another way of doing it. And the seconds cancel, the minutes cancel here. You multiply by 3,600, and you get a number like 1.4 times 10 to the 6th miles an hour. I think that's pretty fantastic. Just putting an electron in a 1 volt, giving it 1 electron volt of energy will change its speed by about 1 million miles an hour. I think that's pretty astonishing. Of course, if the mass were different, it would be different. You would put in a different mass here. So you could do this for any charged particle or anything like this. But this is in free space. This is the key thing here. This is in free space. It will accelerate and go like this. So this is 1 volt. Now you have to figure what they do with atom smashing machines. The one at CERN, the one that's famous, the CERN Large Hadron Collider. The voltage they put on there, it's hard to believe, but they're aiming for 7 teravolts. Tera is trillion. They're trying for 7 trillion volts. So the speed, if you're naive, you'd say, I'm going to go 1 trillion times that. That's 10 to the 12th times 10 to the 6th. That's 10 to the 18th miles an hour? No. What happens, of course, we run into relativity. And because that would exceed the speed of light by a large amount. And nature doesn't allow that. So, in fact, that 7 trillion volts does not result in 10 to the 18th miles an hour. It ends up like the speed of light, which is 186,000 miles an hour. But the interesting thing, I looked it up, they say that with that energy, you can get within the speed of light less 3 meters a second. They get it up to almost the speed of light. It's just going 3 meters a second slower than light at that speed, but you can't quite get to the speed of light. So it's an amazing thing, but I just want to put it in context. So a volt can mean quite a bit here. But the other thing that I want you to notice, that's a large number, but that's in vacuum. Now we're going to completely switch gears and start talking about putting these voltages not on a plates on a empty space, but we're going to do something like this. We're going to put the thing on a material, and that's a whole different ballgame. This could be a conductor, or a poor conductor, and so on, all kinds of things. But it's going to be a whole different ballgame. The reason being that here the electron going from here to here felt nothing but empty space. All the force that it felt was that of the electric field. On the other hand, if an electron is trying to get through a material, it's got to get past all the atoms. And the atoms are not always lined up very nicely. And moreover, the material is warm, so the atoms are moving around. So the electron trying to get through runs into resistance. There's the word. It runs into resistance in passing through a material. And that's a very important concept. I don't know, it seems to me a very intuitively obvious one, but that's what this setup is supposed to show. Let's see, I wanted to just set up the difference between wanted to set these two planks more or less at the same angle, and I have marbles here. I hope I don't lose my marbles. Yes. Okay. But I have one. Yeah. Now, on a smooth plank like this more or less simulates going down a potential barrier with no particular obstacle. So it goes down pretty fast and accelerates and stops at the other end. So we could have calculated, in fact, that final speed or something like that. Now, compare that with this. See, now this is a thing going in a material, and it keeps bumping into the atoms, and things are... Oh, this is like a pinball machine. The ball came back. Cute. So that's the difference. You see here, this is a material thing. Let me try to set them off at the same time, at the same height. Just again, obvious thing. This guy is still struggling here. Yeah, so that's really the difference between a material and a vacuum. So, but the other thing that you see is that this thing sort of ended up going at a constant speed, more or less. It's sort of like going down in a parachute. If you jump out without a parachute, you'll accelerate presumably all the way to the ground. There may be some air resistance which will slow you down. But in principle, if it were vacuum, you'd speed up and keep speeding up. On the other hand, if you increase the resistance, which is like the air resistance of the flow, you end up going at a constant speed because the force of gravity is balanced by the force of the air resistance. And so you end up going at what's called in those terms terminal velocity, the final velocity that you have. So this is a very instructive thing because if you look in detail at what's going on, every time the thing hits a nail, it sort of loses its speed, but in between the nails, the gravity is acting, so it speeds up. Then it hits a nail, loses its speed, picks up again. So it's going speedy, stop, speed up, stop, speed up. So that's the model that we can use to try to understand electrical resistance. Now, I think I have written this. For those who haven't seen that demonstration, we did something like this where we had dissimilar metals, and we found that there was a voltage difference across them, a potential difference, and showed that. Okay, now here's the point that we have. We have one of these voltaic cells here, which can create a plus push. and pushes charges. By the way, the direction of the current is the direction a plus charge would move. That's a convention. Again, it's a definition that you have to know. Unfortunately, in most materials, it's the negative charges that are moving. But somehow we stick to positivity, think positively, and we define the current flow as the direction a positive charge would flow, so that if you had a cell, dry cell, with a plus thing here and negative here, we, by convention, say that the current will flow out of the plus, because they will be the pluses would be repelled, and they will go around, and then you have some kind of an object here, a solid material, a resistor, which we symbolize again by something like that, indicating it's a hard way to go, and it comes back to negative, like that. So it's a complete circuit. So this battery is applying actually a voltage or a field. It actually is providing energy. There's a voltage different, actually called an EMF, that is acting the way I acted when I lifted this thing. I put energy into the system. Right? It was I who lifted that up here. And I gave it potential energy, which is then converted into motion as it goes down. But also, the fact that it bumps into the nails means that it's delivering some energy to the nails. That's where the potential energy is going. So there's no particular increase in speed here. So the general idea of an electric circuit is that you apply a push, or you provide energy, you lift the charge up to a certain energy. It then loses the energy in the resistor and comes back with no energy. And if you have a generator, it will charge it up again and send it on its way with more energy. So here we're working with the case that, unlike the upper picture where we had objects in electric fields, but they were finite, and so the current could flow, yeah, but they would stop at some. And we always said, let's go to the static condition. Here, we're not doing that anymore. Now we're saying, okay, let me put a field on, but let the current flow. And that is, and also it's going to be flowing through a material, as I say at the bottom here. So we have to understand that we have here something has to cause the flow. And I make an analogy with water, a very familiar analogy. You'll see it in your lab notes, that with water, for example, the analogy is lifting water up to, say, a water tank, and then allowing the water to flow down, in which case, for example, it could turn a water wheel or something like that, but its energy, potential energy, its height, is analogous to the voltage. And if you have a pressure or height difference, or a pump that can lift the water to a high place, then you've given it energy. And the analogy with electricity is this electromotive force. It's this difference between the traction in different metals. And there are many, many sources of this EMF. We have the dry cells. We have wet cells. Like the dry cells are your ordinary dry batteries. The battery in your car has sulfuric acid, a liquid, and metals and all kinds of stuff. So it's a wet cell. You have electric power company, provides you 120 volts, ion pumps in your membranes, power supplies that you use in the lab create voltages, solar cells, light comes in and a voltage appears across something. We'll understand that later. You can get electrical pressure also with the Van de Graaff. That also put charge up here, and there's a pressure for that charge to move. And there's things called fuel cells. So there are lots of ways of creating this pressure. And now the other concept, the next concept, after we cause them to flow, how do you describe the flow of this stuff? Well, in water, we can speak of a pipe that is carrying a certain number of gallons per second, say, through the pipe. You know, you stay here and you see how many gallons go by. That's one way, or the number of liters that go by, or even the number of moles of water that go by. In the case of electricity, we measure the number of coulombs, the slug of charge that passes through here. So the electric current is defined as the amount of charge that passes over the time that it passes. It's like coulombs per second. And that has its own special unit because it is so common, and that is called the ampere. Again, named after a French scientist, Ampere, whom we'll encounter later and understand why he's so famous. So that, and an ampere is if 1 coulomb passes a place per second. That's an ampere. Or sometimes we call it amps, right? Amp, for short. Okay, and so if we have a wire, what's happening? Well, see, we have the picture here. He's trying to talk about conventional current. So he's showing positive charges moving. In most real cases, it won't be the positive charge. It'll be the negative ones. But the direction of the flow, it's from left to right, is this VD, they call it, V drift. You'll see why. Well, it's why is because that's the speed the thing is jiggling through the material. It's not the speed in between the nails. It's the average speed going down the wire. So there's an average speed, although the speed in between the collisions is variable. But we have the general idea of a current being a coulomb per second. One thing about these things is that you could think of this as a pipe with carrying water or charge, but you don't lose any charge. So if you come to a junction or a split, the total amount coming in must equal the total amount coming out. That's known as continuity of current or conservation of charge. We don't lose any. So that's all that slide is trying to say. I'm going to move on quickly. If you like, you can look in my notes, and there's an example of how, if you have, say, 3 amps coming in to that junction here on the left, lower left, and 2 amps going in, what happens? Well, in the wire coming out of there must be 5 amps, because you have 3 coming in, 2 coming in, 5 must go, et cetera, et cetera. You can just follow and see. And the question is, how much is coming out here? Well, if you got 5 here and 4 here, 5 here, 4 here. Well, let's see. You probably have to get 5. Let's see. I don't know what 4 means coming in. 2 here, 4. It'd be 5. Then 5 has to split. You have 1 here, so you have to come back. So it was 3 out of here. Means there must have been 3 here. And out of 5, 2 must have gone here, which counteracts 2 here. So you got 2 here, and 2 here. Well, just add them all up, and somehow it has to come out 8 amps. I'm going through it too quickly, but that's the kind of game you have to play. Okay. Now, this is the demonstration I just gave, and we want to use this to understand why, do a little more quantitative thing about why the speed ends up with a constant speed. And the constant speed will be proportional to the height through which the thing drops. So I go through a derivation here. Do I have time to go through it? 15 minutes. Probably not enough time. I'll post this. I must say it's not in your notes right now. But the idea is simply to go through and say, In other words, let's think of this system here, where you have all these nails, and the thing is speeding up. It has an acceleration between hits given by the force over the mass. So you put in the force. In the case of the electric field, the force is QE over the mass. But the thing is interrupted. Every couple of seconds, it runs into a nail. So the average velocity is equal to the acceleration times this time, the scattering time. So that you end up with a sort of an average velocity given by this acceleration times the scattering time. And then you just have to say that my current is somehow related to this drift velocity, because the current is proportional to the velocity times, say, the number of carriers and their charge. That's going to be the current. Well, it's proportional to, if you go through this derivation, you'll end up with this law that it's going to come out that the current will not be accelerating, but it's going to just be proportional to the change in voltage. But inversely, as some constant R, so that if you have a given voltage, if the resistance is high, the current will be low. And the resistance has two parts to it. Let's say L. The resistance has two parts. It has a geometrical part, namely the resistance will go bigger with the length. Surely if you have more of this stuff and you have to get through it, it'll be harder to do. And it'll go inversely as the area. The bigger the area, the easier it is to get through. And then it has something to do with so this is the geometrical factor. And then you have to have the materials factor, the particular material. In other words, if it's copper, the material will not resist very much. The electrons flow nicely. On the other hand, if you have something like graphite or lead, this intrinsic material property is called the resistivity. And this resistivity contains the factors that reflect that scattering process. So let me write down, just for your, just to make it more obvious perhaps, the resistivity is a materials factor. It depends on the mass of the particle that's moving, the number of them, the square of the charge, inversely as the scattering time. Now, this is derived in my notes here, but the point is it's pretty obvious that the shorter the scattering time, the more resistive it is. In other words, if the thing is bumping quickly, the resistivity, this material, is stopping the charge more. The more massive it is, the harder it is to get through, so the resistivity should go up. And the more charges there are, N is the charge density, Q density per unit volume. If you have a lot of charge, then the resistance should be low because there's a lot of them going through. So that's a pretty reasonable formula, and it's derived sort of in the way I indicate in that slide, which I will make for you. It's in the book, I believe, someplace. Okay, so what this all comes down to is this particular law, which is called Ohm's law, and it's the crucial thing that we need. And it's very plausible. This represents the amount of push you're pushing on the charges. This represents the material trying to stop the flow. So the bigger the resistance, the less the current will be. So I have another slide here where this resistance as a quantity, the analogy with water, there really is no word exactly for it. I call it clogginess, the clogginess of the pipe. In other words, if you have a clogged pipe, the resistance will be high. All kinds of stuff, you've had clogged pipes. Okay. If the clogginess is high, the resistance is high, the flow will be low. Even though there's pressure, the flow will be low. So the resistance is sort of like the clogginess. There's another term we've just defined, clogginess. But you can think of it that way, and it's perfectly right. And so this just says it again. That is that the current will be proportional to that. Now this unit for the resistance is V over I, so that would be volts per amp. But this unit is so often used that we actually have the unit, a special name for it, the ohm, after Mr. Ohm of the Ohm's law. That's an ohm, and it's symbolized by capital omega. So that's the unit of resistance. And what happens, again, is that as the charge goes through a resistor, it bumps into the resistor and it loses its energy into the resistance. The amount by which it drops its energy is actually given by. So, and this you use a lot. If you have a resistance and a current is passing through it, Ohm's law applies here, and the change in the voltage on this resistor will be I times the amount of this resistor. Now, conventional current goes from plus to minus. You see, because you started out with a battery like this, and you push plus charges out, and they go through, so we speak of this delta V as the voltage drop, because it drops from a high value to a low value. The potential actually decreases. But if you don't speak of because then you would say delta V, the final voltage is lower, so that this delta V would be negative. That's the change in V. This is a little tricky. But the drop is a positive drop, because it does go down. So the drop is positive. So that's the way the engineers and physicists talk about it. They speak of the voltage drop across something. It means it's going from plus to minus. It's decreasing, it's dropping, so it becomes kind of a positive quantity. It's a little strange with the signs, but so each time it passes through a resistor, it loses. What happens is you connect the battery to the resistor. The current builds up until you're losing as much energy as the charges had, and they come back to this point. This is a very important point too, namely that all things on the wire, there is no change in the voltage. There's no loss on here. So every point on here has the same energy. On a wire, a good conductor. We're basically, the resistance is zero. So delta V being IR, if R is zero, there's no voltage drop on the wires. This is an approximation, because wires, in fact, do have resistance, but unless we say otherwise, we're going to assume that the wires have zero resistance. So that when the current comes back here, it has the same energy as this point. See, because it's on this wire, and this wire is connected here. So all of the charges have the same energy up to and including that point. And then, of course, your electromotive force boosts up the thing and gives it more energy. So what we think, the way to think about it is that this electromotive force boosts up the energy. It goes here, doesn't lose anything, reaches here, loses all its energy in the resistor, has no energy compared to here when it comes back. So that's the way to we think of this. Now, the thing that you will be faced with in the lab and in other problems is that what happens if you have more than one resistor? For example, suppose you have two resistors. And let me show you what resistors look like. They could look like. For example, these are resistors. See, what it is it's two connectors here, and inside of here, I think these are wire wound. So there's a lot of wire. So what you got is the long length of wire, so that it impedes the flow of current through this wire wound. And here's another one. This one has 4,000 ohms. This one has 3,000 ohms. They look alike, but it's written on there how long the wire is what its resistance is. So the question is, what do you do when you have something like this situation? Yeah. Let's see. Front row, maybe. Make things any clearer. Can you see these meters back there? Oh, the other thing I have to tell you, unfortunately, is more and more stuff. It's really simple, but there's just a lot of little things. Namely, that if you want to measure the voltage drop, just like if you want to measure the height of the water, you have to go to the top and the bottom of the water. So if you want to measure the voltage, you have to go across it. Voltage is always measured across because it's sort of like the height. And you have to know the top and the bottom. On the other hand, if you want to know the flow, the current, you want to be in the circuit. You want to be right in here to see how much is going through. So to measure voltage, you want to be across the thing. If you want to measure, you have to be in the line. So we have 2 meters here. This one, this is the one that's in the line. See, because here's a battery. I'm going to put a voltage across here. This is the source. It's going to go through. Now, you see how this guy is right in the line? I'm going in here, out here, in here. So this fellow is measuring current. Because whatever flows in here is going to flow through the meter, through here. So this is an ammeter, ampere current. This allows me to go across the thing. So I'm measuring, since the height of the voltage drop across these. This you really have to know. So if you measure the voltage, like if you go to your socket there and you want to measure the voltage, you're measuring when you put your voltmeter in, you are putting it across the line. So let me, for example, now we have a circuit where the battery is going to push current through here, through these 2 resistors, then through this one back to here. And we have 3 somethings. I don't know exactly what scale it's set at. Now, if I want to measure the voltage, first of all, let me measure the voltage of the battery. Let's see. Oh, 12 volts. Okay. See, I'm going across the battery. Let me go plus red to red, black to black. 12 volts. You see, that's what I'm putting. That's the push through there. Now, as I say, when you come all the way back, you should get 12 volts. So part of it is dropping over here. Let me measure that. Let's see what... This should add up to 12. Between here and here is something. Ooh, not much. Maybe half? Okay, but how about between here and here and here? Ah, there's where it is. See, that's 11. So between the two, I've added up. I've added up to the voltage around the whole circuit is back to the voltage that I put in. Now, here's the one tricky thing that I'll leave you with. Suppose I take this out. Will the current go up or down? This is the tricky thing at first. Namely, look, here the current has two paths to go. So this is a low resistance path. If I take this out, I'm taking away one of its paths. I'm making it harder for it to flow. So the current, I think, should go down ever so slightly. Put it back in. Should go back up. Let me try this one. Yeah. So that's known as your parallel connection. I think you'll learn more about this in your lecture, your labs and discussion, I hope. We'll continue on Wednesday, too.